All right, so a little review of chapters 5 and 6 for trigonometry. We have these ideas called the sine of an angle, cosine of an angle, tangent of an angle. And that angle theta, it's either within a circle between radii or from a triangle. So we'll take both perspectives here. And we'll get to the idea of an inverse trig function. So some circle centered at the origin. I take some radius out here. That forms an angle with the positive x-axis. So whenever we start with the positive x-axis and measure the angle, that's called the standard form for the angle right there. So there's my theta. Now that leads to a point here on the circle. There's a radius that leads out to the point, and then we have coordinates x, y. So the first time we define sine, cosine, and tangent is given an angle. What the sine tells us is the ratio of the y value to the radius. Cosine tells us the ratio of the x value to the radius, and the tangent tells us the ratio of the y value to the x value. So these trig functions connect the angle to the x and y coordinates and the radius together. Now, the tangent, again, has another special interpretation. It's also the slope of the radius there. Right, we have our y over x. Triangle-wise, if I drop a perpendicular from this point, that perpendicular I drop there is the y value. That y value is opposite that given angle, right? It's across from opposite. The bottom leg of this triangle happens to be the x value of the point there. And that length there, that x value, that side is adjacent or next to that angle. So sometimes when we're talking about these ratios, we talk about opposite versus adjacent. Sometimes we talk about x and y, kind of depends on the context. With respect to opposite and adjacent, this radius is also called the hypotenuse, right, of the right triangle. So another way to define the sine here, instead of calling it the y value for the numerator, we call it the opposite side. And r is the hypotenuse. So we have two different interpretations. They're basically the same thing. X value would be the adjacent side in that triangle. R is the hypotenuse. And then y, again, opposite, x adjacent. So summary, what a trig function does is it turns an angle into a ratio. So that's what trig functions do. Different trig function is a slightly different ratio, but they're all the same angle in some triangle or inside some circle. Inverse functions, on the other hand, just reverse that procedure. So any inverse trig function turn ratios into angles. So let's look at some specific examples of that. Let's think about our first quadrant. That was not a very good quarter circle. Let's do better this time. Oh, marginally better. So there's my quarter circle there. And then we have our special angles. That's about pi over 4 there. Pi over 6 should be about there. Pi over 3 would be about here. So we have our angles out to here, 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and up here pi over 2 radians. And then the corresponding points if we're on the unit circle. So let's say x equals 1 here, and y equals 1 to make it simpler. Then the points, 1, 0, square root of 3 over 2, 1/2, square root of 2 over 2, square root of 2 over 2, 1/2, square root of 3 over 2, and hopefully this is burned into your memory. So this unit circle tells me a few things. It tells me, for example, the sine of pi over 3. I know that's the y value over the radius, and I chose the radius here to be 1, so it's just the y value at that point. Y value would be the square root of 3 over 2. The inverse sine, we just switch that. So if I look at the inverse sine takes a ratio, like square root of 3 over 2, and outputs an angle, like pi over 3. Right? The angle is the output for a trig, for an inverse function, instead of the input. So inverse functions give us an angle. In this case, radians. Regular trig functions, angle input. Right? Inverse functions just reverse that. We have another name for the inverse sine. It's also called the arc sine. So arc sine of square root of 3 over 2. Because we know our unit circle very well, we know that answer has to be exactly pi over 3 radians as the output. Sometimes we like to call it in degrees, but radians are more useful in trigonometry. Degrees are just something we're kind of stuck with because of history. So we could say that's also 60 degrees. Right, so again, what's the point of inverse function? Inverse function is to find an angle. Example where we might want to do that outside of the circle, kind of the most popular, I would say, of using inverse trig functions. Is when we have some lengths related to a triangle. Like suppose I have this triangle right here, and I was just attempting to make this side about 3, a right angle there, and I was attempting to make that side right there a 5. And I want to know, what is this angle right there? So this is a good example of where we'd use an inverse trig function. We know we want this right angle right there, and we need to say maybe put a brace here, or have some kind of tie rope connecting these 2 points here and here. How do we determine what that angle is? Here I have the side opposite and adjacent, and I'm thinking, okay, opposite and adjacent, that would be tangent. So the tangent of that missing angle would have to be 5/3, right? Because the 5 is opposite, 1/3 is adjacent, the 3 is adjacent, excuse me. So to get that angle, I have to apply the inverse function, arctan or tan inverse. Can whip out a calculator, get a measurement on that. And sure, I wanted the other one though. Let's see, graphing, there we go. So I want to know, what is the tan inverse? 5/3. And I get about 1.03-ish radians. And if we wanted that measurement in degrees, just switch our calculator mode. About 59 degrees. Oh, get back here. And my picture's not perfectly accurate, but it's not too bad. So I would say, yeah, that looks reasonable. 59 degrees seems okay in there for my remembering about what degrees look like compared to, say, 90 degrees or 60 degrees. So again, inverse trig functions just take ratios, turn them into angles. So anytime we need an angle and we have some information about ratios, parts of a triangle, we can use an inverse trig function to figure out what that is. Now, given that trig functions are inverses, they cancel each other out. So if I were to do something with the right values of like the cosine inverse of the cosine of pi over 3, then the answer should be pi over 3, right? Cosine takes in an angle, inverse cosine spits out an angle. Since these guys are inverses of each other, they ought to cancel each other out. Now, as far as the output of the cosine inverse, remember they have a limited range. And just a reminder about that limited range, if we take a look at, switch back to radians, things graph correctly. If we look at y equals the cosine of x here, the problem with this function is it keeps oscillating like this forever and it doesn't pass what's called the horizontal line test. So it is a function because it passes the vertical line test, but its inverse is a problem because of the horizontal line test. So if I just try to switch x with y and graph x equals the cosine of y, that's going to give me an inverse relation here. But this green thing is not a function. So we have to cut off parts of it so that it is. So anytime it turns back on itself is a problem. And the standard way to cut it off is just to say, okay, you are only allowed to give us angles from an output of 0 radians to an output of pi radians. Because once we go through that turning point there, we fail the vertical line test. It's not a function anymore. So important thing to know about cosine inverse. It has an angle range of 0 to pi. Whereas the sine and the tangent are different. The sine inverse or arcsine and the tan inverse or arctan, they have angle ranges from negative pi over 2 to pi over 2. And let's see, for the sine, we actually get the possibility of negative pi over 2 or pi over 2. Tangent, we do not because of the asymptotes. So we have parentheses there. So what happens if I try to compose a trig function with an angle that's not in the inverse function's knowledge? So for example, if I try to do something like cosine inverse of the cosine of something past pi out to the or a negative value, let's do negative pi over 3. What's going to happen here? What's the arc cosine going to say about that? You could whip it in your calculator and see. The calculator will give us an approximation of something, but unit circle will help us figure this out too. So negative pi over 3 would put us, so negative pi over 2 would point straight down. Negative pi over 3 is going to be, say, right over here. So that angle right there is negative pi over 3. That gives me this point right there. That point right there, cosine is dealing with x values on the unit circle. So since we're dealing with cosine, it's related to this x value. What other point on the unit circle has that x value? Well, it would be this point up here has that x value. And so what other angle is related to that point? Well, I can just draw in that radius, and it would be this angle right here, which happens to be positive pi over 3. And remember, the inverse cosine only understands angles up here. So if our original cosine function starts with an angle elsewhere, the arc cosine is going to translate it to what it knows about, and pi over 3 is in its language. So what I should see if I whip this into my calculator, I should get pi over 3. So with respect to my original statement out here about the cosine inverse and the cosine cancel, that's only for angles within its realm of knowledge, and it only knows about angles between 0 and pi. Otherwise, it has to do a translation. So let's check that out in the calculator. So we can either use arc cosine or cosine inverse of the cosine of, I started with negative pi over 3, and what I should get for an answer is the value of pi over 3. So we can enter pi over 3 to make sure that matches. And so I can see there's the same value. So inverse trig functions are super powerful in that they allow us to solve for situations where we don't know what the angle is, but we had other information. However, they're limited in that they only have certain angles that they can work with. And so sometimes we need to do a little other geometry to find other angles that might be related to that. So let's do another example of that. Let's suppose we had a situation, we had to solve a trig function. And let's try twice the sine of theta is equal to -1. And we want to solve theta, and we need first 3 positive solutions for this situation. So we can graph this and see there's going to be a whole bunch of solutions. So let's clear. So to check on solutions like this, I just graph the left side twice the sine. I have to use x here. And the other side of the equation was y equals -1, which we have to actually type y equals. And so I can see here that there's a whole bunch of positive solutions. There's this one here, there's that one there. Desmos is nice. Whoa, I don't want to zoom out that much. I want to drag it over. Gives me exact values, which is cool. So let's see if we can confirm those exact values there. So we solve this like any other equation. We need to unwrap it. So we get rid of the 2 first, dividing the 2 to the other side. Sine of theta is equal to -1/2. And I'm thinking, oh, that is one of my special ratios on the unit circle. So think about the unit circle for a moment. On the unit circle, sine is a y value. So this says, okay, where is sine equal to -1/2? Well, that would be either this point over there or that point over there. Now I can get to this point right there by sweeping a negative angle. I could also get to that point by sweeping a positive angle. So there's 2 ways at least I can get to that particular solution here, that particular point. And then the other one I can get by just sweeping down like this to get there. And then I can just add multiples of pi over 2 to either of those to generate more solutions. So I have 2 fundamental solutions here, and then I can use the domain, the period to get as many other ones as I want. Now, remembering the unit circle, I recall that to get that y value right there, that reference angle is going to be pi over 6. Now, since I'm sweeping in a negative direction here, I could call that angle negative pi over 6. So I could say theta equals negative pi over 6 would be one solution to this equation. I can plug that into my calculator and check. Now, I want positive solutions here. So to get the positive version of this one right here, I just think if I rotated around a full revolution, but then backed off that amount, I'll get what I want. So the positive version of that solution right there, so let's call that theta 1, would be 2 pi minus that pi over 6, right? Go around once, but then back off that amount. So let's see, what would that be? 12 pi over 6 minus 1, so that should be 11 pi over 6. Should be this particular point right there on the unit circle. This other one right here, well, the reference angle there is also pi over 6, right? Reference angle is the angle to the closest part of the x-axis, so I just need to go pi farther. So I'm going to call this one theta 2. These aren't necessarily in order. If I just take pi plus pi over 6, that gives me another one. So that would be 6 pi over 6. So 7 pi over 6 is another solution. And although I call them theta 1 and theta 2, that's just the order that I came up with them thinking about this angle over here. But obviously 7 pi over 6 is the first in order here. Positive 11 pi over 6 is the next one. So just rethinking that. If I want them in order, I'm trying to get to, remember this is here, y equals -1/2 from where I solve for the sine up there, either this point or that point. And if I revolve around in a positive direction, which I was asked to here, then I'm going to hit this solution first. So first thing I'm going to do is hit 7 pi over 6 as a solution. I keep revolving around, I'm going to hit 11 pi over 6 next. And if I keep going around, I'm going to come to another version of that one right there. And that one right there is just one revolution more than I was already at. So my claim is that if I take this one right here and I add 2 pi to it, that's going to be the next solution I want. So my theta 3 is going to be that 7 pi over 6 plus another period. That multiply top and bottom by 6, that's going to give me 12 pi over 6. 12 and 7 is what, 19? So 19 pi over 6 should be the next one in order. What solution is the arc sine going to give us? Thinking back here, the arc sine only knows about angles between -pi/2 and pi/2. So again, the arc sine only knows about angles between -pi/2, so that would be heading that way to there, or +pi/2 that way. So what the arc sine is going to give us is this one right here, which turns out isn't one of the ones I want, right? So I had to use a little translation on the unit circle to find some other ones. All right, let's do one more inverse problem. If we invert the other way, some interesting things happen. So suppose I have the, let's make it a little more interesting, the cosine of the sine inverse of 2/3. So what does an inverse function do? Inverse function outputs an angle. So the result of this right here is some angle, theta. So I can rewrite this statement right here by saying, if the sine of theta is 2/3, then what is the cosine of theta? So that'd be a restatement of that, right? Because the sine inverse is an angle. Now, to solve the sine inverse is 2/3, I could either draw a circle, kind of like I did before, find y equals 2/3, see where it leads to, see what the cosine is, or I could draw a triangle. So either way works. I'm going to do the triangle route because I already did some circles. If I think about triangles right here, then I have to remember sine is opposite over hypotenuse on a triangle. So if I draw a triangle, let's see, opposite is 2, hypotenuse is 3, so maybe it looks something like this. Right angle. All right, and usually my first draw on one of these triangles isn't the best, so I'm thinking that this is, if I put theta here, this side would be opposite, so that's my 2, and then this should be 3. Close enough. Now the cosine, to figure that out, cosine is adjacent over hypotenuse. So I just need to know, what is this adjacent side here? Pythagorean theorem helps us figure that out. Pythagorean theorem says if we take that adjacent side squared, add it to the opposite side squared, that ought to be the hypotenuse squared. So 4, 9, subtract the 4 over, we get a 5. So the adjacent side squared is 5. So the adjacent side itself has to be the square root of 5. So now I know that the cosine here ought to be that adjacent divided by hypotenuse. So the answer here ought to be the square root of 5 adjacent over hypotenuse 3. And we can test that out on a calculator, see if it works. So we are looking for the cosine of the sine inverse 2/3. And computer claims that's 0.745-ish. And we believe that is the square root of 5, then divide by 3. And those look like the same number to me. Cool. Inverse trig functions operate in many different ways.